Hello, Chem students. I'm going to discuss the first half of Chapter 2, which covers physical properties, polarity, types of bonding. These are important ideas. We'll start off with just talking about what is a melting point and what is a boiling point. A melting point is where the solid form of something has enough energy to start to break down the lattice and become a liquid. In a liquid, the order is a little less. Usually the solid is very compact and all the molecules or atoms are close together in an ordered arrangement, which is called the lattice structure. But in a liquid, some of these escape out of their lattice positions. So they say about 1 out of 10 molecules is displaced. And that makes it so these holes can be filled in and move around, and that gives the liquid its ability to flow that we associate with something like water. Okay, now that's going to take energy to do that. So the melting point is a particular temperature, usually specific, pretty narrow, where this starts to break down, and all the energy goes into breaking that down. Once you melt something, then the liquid will start to heat up, so you'll keep adding heat. The motions here will become more and more vigorous until we reach a point which is called the boiling point. And at the boiling point, each separate molecule or atom escapes from all the others and becomes sort of independent all by itself. And generally it's assumed in the ideal case that these particles are so far apart they don't feel any influence by their neighbors. And that's not exactly true. But we have what's called the ideal gas law, which you probably studied in freshman chemistry, PV equals nRT. And so that's used a lot, although there are real parameters that account for some of the imperfections of the ideal gas law. But we're not going to study any of those. That's more of a freshman chemistry topic. Okay, now as far as predicting a melting point, that's a little bit difficult to do. It depends a little bit on the strength of interactions between the neighbors, but it also depends on how well they can pack together. Usually more regular shapes and symmetrical shapes pack together closer and tend to have stronger forces, and then the melting point's a little bit higher, sometimes quite a bit higher. When we go to the liquid, that whatever the forces of interaction are here, they're going to be similar to the forces of interaction here. Just a little bit less because some of the molecules or atoms have moved out of the tight lattice structure. But the huge jump is when we go from a liquid to the gas, because that means all of the forces of interactions between the neighbors have to be overcome so that each molecule can become independent of all the other ones. And so this is actually a very good temperature to measure the strength of interactions in the material, the liquid in this case. And that's what we'll use it for. Now, there's one very special liquid, solid, gas, one very special substance, and that's water. Water is different than almost all of the other stuff that we look at, because in general, solids like this over here are more compact than the liquid's more dense. And so if you had something that was solid in its liquid, it would sink to the bottom. But as we all know, ice does not sink to the bottom. Ice floats on the top. So the difference is, for water tends to make these very strong hydrogen bonds between a hydrogen and a lone pair, and between a lone pair and a hydrogen, lone pair and a hydrogen, hydrogen and a lone pair. And so all the water molecules around a particular water molecule are kind of pushed out a little bit to make this structure, this lattice structure of the ice, and that expands it out so that it's not quite as dense as the liquid. And since it's not as dense, it floats on top. Its density is around 0.9, whereas the density of water is around 1.0 in terms of grams per cubic centimeter. And so ice will float on top of water, and about 1/10 of it will stick out. 9/10 will be under the water. Okay? So that makes ice very different, which is fortunate for our world, because that means when ice breaks off of a glacier or an iceberg floating in the ocean, it's on the top. And so the sun can melt that and keep basically everything liquid, as opposed to just having solid ice at the bottom and then a little bit of water on the top that melts, say, in the summer. So this has actually made our world very different. Now, in fact, water in our world can be boiled, can actually go into the vapor phase, and so then we would have water molecules very far apart from each other with no attraction in the ideal case, no attraction for the neighbors, and that would be the PV equals nRT equation we could look at. Of all the liquids that we have in the world, water is one of the very few that has a solid form, a liquid form, and a vapor form in our particular environment of the world. And not to mention that water is the solvent of life. Okay, we're going to start off with ionic bonding. And ionic bonding is extremely strong bonding because the participants have opposite charge. So we have cations and we have anions. And probably the most familiar one that everybody knows about would be like sodium chloride. So sodium plus cations plus 1, chloride minus anions. And the melting point and the boiling point are extremely high. If you look at the melting point, 801 degrees Celsius, boiling point for over 1400 degrees Celsius. Okay, you are never going to put your salt shaker on the table and come back and find that it has evaporated. Okay, that salt will stay there as long as you have it there without shaking it on your food. Okay, so that salt's not going to evaporate. Now, the property of sodium chloride is very different than the property of the things that it came from. Sodium metal is a very soft, pretty low melting metal, 98 degrees, that's less than the boiling point of water. Still a high boiling point though. The melting point's fairly low though. And then chlorine is a gas, sort of a greenish colored gas, very, very reactive. In fact, it was I believe it was the first wartime gas ever used back in World War I by a German chemist who basically released chlorine gas and let the wind blow it towards the enemy lines to poison them. So not a particularly good use. But chlorine has a very weak bond since both of the chlorines have to share with each other and they don't like to share because of their electronegativity. Sodium, on the other hand, is not electronegative, it's electropositive and wants to give its electrons away. If you were to take sodium metal and mix it with chlorine gas, probably the result would be an explosion. They're so reactive and you would end up with a lot of sodium chloride. So this is basically a thought experiment. It's not something we would really do. If we look at the electronegativity difference between these two, chlorine's pretty electronegative, 3.2, and sodium is pretty electropositive, 0.9, and the difference is 2.3, which according to our rules, anything over 2 is ionic. And remember, if it's ionic, it's going to have a very high boiling point, and probably a high melting point too. If you were to look at sodium metal, which maybe you've seen before, maybe you've got to play with it. Okay, it's pretty soft. It's kind of exciting to play around with. If you took a little tiny piece and put it into water, it would start dancing around on the water and catch on fire. It would generate hydrogen from the water and oxygen. So it would be extremely reactive and might, if you took a big piece, it might blow up on you. Chlorine is a poisonous green-colored gas. Okay, has a lot of uses. Chlorine's very useful in our world, but it's not. You wouldn't want to work with it as the gas. It's very dangerous. If you mix those two together, then we end up with sodium chloride, and everybody has seen sodium chloride in salt shakers on tables everywhere, at home and restaurants. Okay, and generally a lot of people like to flavor their food with it, but you got to be careful. Too much in the blood can possibly lead to high blood pressure. So even though it tastes good, you can't go crazy with it. We're going to look at all ionic substances in this simple-minded picture right here. This might be a lattice structure for something like sodium chloride. What you'll notice is that each ion, say this anion here, is surrounded on all sides by the opposite charge. Cation, 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 cation. And if you look at the chlorides, they're all surrounded too by cations, and the anions are surrounded by cations. Okay, so this particular structure is very hard to break down. If you were to try and go in and take out just one sodium and one chloride, you would have to disrupt the whole structure, and that's why it would cost so much energy. Okay, so if we just look at an anion all by itself, you would see it's surrounded. You'd have to overcome all these forces to take that anion out. And a cation would be surrounded by anions all over. You'll notice I drew the anions a little bigger. That's because they have excess electron density, which repels its other electrons, so it's a little puffed out. Whereas the sodium is electron deficient, and that's going to contract and pull in the electrons that it has tighter, and that's generally the way they are. Another possible thing besides the size of the charge is the size of the atom, but we're not going to look at any of those particular details. I put a few examples down here, ionic salts, And I just pointed out they have very high melting points and very high boiling points, and that's because this lattice energy is very, very, very strong. So if I look at something like lithium fluoride, parallel to sodium chloride, +1, -1, has a very high boiling point, 1700 degrees, very high melting point, large difference in electronegativity, okay, because fluorine is 4 and lithium is 1, so very, very large. I picked this one because it's a +2 and a -2, just to show a difference. Magnesium +2, oxide -2. Extremely high boiling point, 3600 degrees. Okay, melting point 2852. That's super high. The difference in electronegativity between these two is 2.2. So again, very large difference. Over 2, we call it ionic. And then I have aluminum nitride. So this one is a +3 and a -3. Okay, so I just tried to pick a little range here of charges to show you. Very high boiling point, very high melting point. But if you look at the electronegativity, difference is 1.4. So you might remember when I made up those rules on electronegativity, I said that even though the book that I was looking at made 2 the cutoff, anything below 2 was supposed to be polar covalent. Clearly this is not polar covalent. This is ionic. The melting point and boiling point are extremely high. And so this is one of the exceptions. Okay, so I have all their electronegativities over here. You can check those out and their particular names. But again, this is just something I'm pointing out as one of the types of bonding. In organic chemistry, we're not going to emphasize this a whole lot. Now, probably everybody here has taken sodium chloride and dissolved it into water, and it dissolves very quickly. That's kind of amazing if you think that to melt sodium chloride requires over 1400 degrees Celsius, yet to sprinkle it into water and separate those same ions can be done at room temperature in a matter of a couple minutes. So there's something really strange going on here for that. Now, in the solid like this, where the pluses are attracted to the minuses, we call that the lattice energy. And for ionic materials, that's very, very high. Okay? So that would be energy we have to overcome if we were going to dissolve it and separate those ions from each other. Now, once we have the ions separated, if we put them into water, water will interact with all those ions and give back a lot of that energy. Because water has a negative end where the oxygen is, and water can surround, say, a cation on 6 sides, top, bottom, front, back, left, and right. And then other water molecules can arrange around those and so forth. And so all of those water molecules interacting with this guy help overcome the energy of this chloride anion that was over here. Now the chloride, on the other hand, also can interact with the water because water has partial positive ends on the hydrogens. And so the water can gather around the chloride at, again, say 6 different areas and help interact with that and give it back energy that it took to separate it away from the sodium cation. Now, you know that sodium chloride dissolves. So the net result of this solvation energy, which is the interaction of the ions with the water, this solvation energy is greater than the cost of the lattice energy, and that's why the sodium chloride dissolves. The overall delta G is a little bit negative. Okay, you might remember delta G equals delta H minus T delta S. So that's a little bit negative. Now, probably in freshman chemistry, you did an experiment where you took something like silver nitrate and precipitated it out with something like sodium chloride. So this is, again, a very similar looking situation in that we have a +1 and a -1. The lattice energy is very, very large. And then if we come over and try and dissolve it, the solvation energy is very, very large, but not quite as large as the lattice energy. And so you'll notice in this case, it looks exactly the same, a +1 and a -1 dissolving in water. But in this case, the solvation energy is a little too small to compensate for that very large lattice energy. And so sodium chloride does not dissolve. It's what we call insoluble. Okay, so just a very subtle difference there. These are small difference between 2 very large values. In one case it's negative, in the other case it's positive. So this is not going to be favorable. So if the solvation energy is bigger, that's good for dissolving. So something should dissolve like sodium chloride. But if the lattice energy is bigger than the solvation energy, that's not good for dissolving, and so it should precipitate or not even dissolve. So let's just do a little thought experiment here. So just stop this for a second and make your guess. Barium sulfate is insoluble. So what does that mean among these choices here? So if barium sulfate is insoluble, then that means the lattice energy is bigger. We don't get enough back from the solvation energy to make it work. Okay, potassium nitrate is soluble. You might remember that from freshman chemistry. So that would mean the solvation energy is bigger than the lattice energy. So we get more energy back than it cost us to break down the lattice. Okay, we're going to look at some covalent situations. We have two possible choices, pure covalent or polar covalent. So this first example here would be an example of a pure covalent molecule. So I picked two hydrogen atoms. Neither one of these guys is very happy because they want to look like helium. They want to have two electrons. So if I had two hydrogen atoms like this, they would immediately bond together to share their electrons to make a hydrogen molecule, hydrogen gas molecule. Okay, and that would release 104 kilocalories per mole. That's a tremendous amount of energy. Okay, it's very large bond energy for such a tiny little molecule like this. Now the difference in electronegativity, since they're both the same, would be 0. So the charge would be equally distributed between these two hydrogen atoms. If we turned it around, well here, if we made the bond, we would release 104 kilocalories. Remember, that's a negative value because we're getting more stable than we were up at the top. So that releases, that's like you get paid $104,000. Now if we come down here, we could imagine the bond breaking two different ways. We could imagine it breaking homolytically, which is kind of the reverse of what we did up here. Each hydrogen atom takes one electron, and that costs us the bond energy, plus 104 kcal per mole. So that's like spending $104,000 to break that bond. Now the other way we could do it is heterolytic bond cleavage, and this is way more expensive. Okay, we're going to take both the electrons and give them to one of the hydrogens, and that'll have a negative charge. And the other hydrogen will lose them both, and it will have a positive charge. And the delta H for this would cost us 401 kilocalories. That is a huge amount of energy to do it this way. Okay, so if we came down and did a little thought experiment like this to see how we might calculate that, the bond energy would be to separate them equally. That's the 104. But now I'm going to steal one electron away from the other guy, and that's going to cost me 314 kilocalories because that electron's right next to that +1 nucleus. Very, very difficult. If you remember back to our ionization potentials, that was the highest ionization potential in the first column by a lot. Now I'm going to take that one electron and I'm going to give that electron to the hydrogen free radical that has a single electron here, and that'll make what we call hydride with a negative charge. This electron is going to get more stable when it gets to associate with the hydrogen atom, and so that actually releases energy, and so we get back a tiny amount of energy for that. They call that electron affinity, and so overall that's 401. So you can see if we're going to break this hydrogen bond, hydrogen-hydrogen atom bond here, we're probably going to do it homolytically because this is just way too expensive. Little analogies that I use, sometimes I look at little calories as being like $1. And if I had 1,000 little calories, that would be like $1,000. And if it's positive, you have to pay it. If it's negative, then you get it in your pocket. So that's a good thing, spontaneous. Or another possible analogy is we're look at 1,000 little calories as 1,000 feet elevation. And we're on a bicycle halfway up a mountain. Okay? So if we have to pedal up to the top of the mountain, plus values, that's a lot of work. Okay, so that's not going to be easy. We have to put in work to do that. But if you're sitting halfway up the mountain and you pick up your feet, you can just coast all the way to the bottom without even turning the pedal. And so that's a very negative value. So yeah, maybe these help you understand energy, maybe not, but it's just a possibility. Okay, so we'll look at some bonds that are important in organic chemistry. Certainly CH bonds are very important. Now, what kind of a bond is this? Well, we take the electronegativity difference, 2.5 minus 2.2, we get 0.3. That we're going to identify that as pure covalent. because our cutoff was anything less than or equal to 0.4 is pure covalent. So we say the electrons are shared evenly in this bond. No imbalance of charge. Okay, and you can see the boiling point is very, very low, minus 162 degrees Celsius. If we go to nitrogen, nitrogen's a little more electronegative. So now when we take the difference, 3.0 minus 2.2, we get 0.8, and that was in the range that was covalent but polar. So they're not shared evenly. In fact, the nitrogen gets more of the electron density. It has a little partial negative because of its greater attraction for the electrons in the bond. And that means the hydrogens are a little partial positive. Okay, so they're going to be kind of like little magnets that stick to each other a little bit. And if that's the case, it should be harder to separate an ammonia molecule from all the other ammonia molecules, and we should be able to see that in the boiling point. And if we come down and look, it's very different. Okay, look at how much, about 130 degrees higher before we can start to separate ammonia molecules from each other. So in fact, this is a representation of that polarity we were talking about. Now if we go to oxygen, oxygen only has 2 hydrogens around it, but again the bond is very polar because oxygen is electronegative. We can see that in its electronegativity, 3.5 minus 2.2. So now the electronegativity is even greater than it was over here. And so that should make for stronger attraction between the negative parts and the positive parts of different molecules, and that should show up as a higher boiling point. And it does, quite a bit higher. Now something about water is that it has 2 lone pairs and it has 2 polarized hydrogens, and so it can grab a hold at 4 different locations around the water molecule, and so it's going to be held to the other water molecules pretty tightly. Okay, in each of those attractions there's a little bit of partial negative, partial positive. If we keep moving and go to HF, well, fluorine is the most electronegative element, 4.0. So we have the greatest electronegativity, and so we're thinking, well, maybe that would be the highest boiling liquid. Okay, so we look up here, we see that, partial positive, partial negative, but when we come down, it's pretty high, but it's not as high as water. Okay, so the difference for the HF compared to the H2O is HF only has 1 H. And so that means there's only one place it can grab a hold of a neighbor molecule with its H. And because all the other neighbors have only 1 H, they can only grab a hold of 1 lone pair over here. And so even though it has a little greater polarity, it doesn't have more attractions because of its single H versus 2 H's over here. Okay? Now the bond energies are all strong. 98, 92, 110. These are really strong bonds. The strongest bond energy is HF, okay, with a plus 135 kcal per mole. Fluorine makes really strong bonds with almost anything but itself, okay, because fluorine wants to attract electrons to itself. If you put it up with an H, it can do that very well, but not completely. Okay, I know this is not ionic, even though we say some separations of 1.8 are ionic, because I can look at the boiling point. Remember the ionic boiling points were like over 1,000 degrees, 1,400 degrees, 1,700 degrees. Okay, so clearly this is probably molecular. All right, so we have 2 ways of breaking bonds. We have the homolytic way, which homo means the same. Each guy gets, excuse me, each guy gets half of the electrons. So we call these free radicals if that was to be the case. And this is going to cost you energy because you're breaking a bond. This is a very comfortable arrangement. We've made it uncomfortable. If you turn that around and look at bond formation, this would be fantastic because I have 2 very reactive free radicals making a very good bond over here with an H. And so that would be a negative value for the bond energy. Okay, money in the bank for you. Over here you'd have to pay for that. So which molecule up above has the strongest intermolecular forces of interaction? Inter means between 2 different molecules. So a methane and a methane, an ammonia and an ammonia, a water and a water, an HF and an HF. Can we tell by the information above which of those molecules has the strongest intermolecular forces of interaction? And the answer is yes, we can. It's going to be the water, because the water shows us that we have to heat up to plus 100 degrees Celsius to separate one water molecule from all the other water molecules. And that's higher than any of these other guys over here. Okay. All right, our next type of bonding is going to be dispersion forces. And dispersion forces go by many names. You might have heard London forces in freshman chemistry. You might have heard van der Waals forces in freshman chemistry. I like dispersion forces myself because it sort of sounds like what's actually happening. Dispersion forces are temporary fluctuations of the negative electron cloud around the atom or molecule. Okay, so the electrons are moving really fast, close to the speed of light. And the nuclei are massive. Okay, so if we come down here and take a look, the mass of a proton is around 1800. The mass of an electron is around 1. Remember, all the protons are in a very, very tiny nucleus. And the electrons are in this massive electron cloud around the nucleus. So the electrons are negative charges zipping all over the place, and the nucleus hardly even moves. So that charge fluctuation back and forth introduces temporary, fast-changing polarities, and that leads to what we call dispersion forces. Now, polarizability is how easy it is to make those electrons fluctuate their electron density around the atom. Okay? And so if we go down a column, it's going to turn out that the larger atoms are more polarizable because they're bigger. And if you go in a column, all the Z effectives are the same. Okay, say we're at the halogens. They're all plus 7. But as you go from fluorine to chlorine, we're out a whole extra layer out, so the electrons on the outside are held less tightly. Chlorine to bromine, electrons are held less tightly. Bromine to iodine, electrons are held less tightly. And so the electrons can move back and forth more, they're polarizable, and that makes for bigger attractions between the neighbors, and that interprets into higher boiling points. Okay, so that's in a column. In a row, as you go to the right, the Z effective gets bigger and bigger. So when you get to fluorine, fluorine's a plus 7 Z effective. It's holding onto its electrons really tightly. It does not want to share them. And so the polarizability is very low. Whereas you go to oxygen to nitrogen to carbon, it gets easier and easier to distort those electrons around an atom. Okay. Sometimes I use a cotton ball to show that. If you stick a bunch of cotton balls together, they kind of stick to each other. It's kind of like having polarizable electrons. They can move around. But if you try to put two marbles together, they're not going to ever stick to each other. Okay, so they're held too tightly, like a fluorine holds its electrons. So if we look at this little symbolic picture here, okay, we would have, say, a nucleus with its plus charge, and it's surrounded by electrons. This could be either an atom or a molecule. It's surrounded by its electrons, and there's no polarity, so we would expect the center of the negative and the center of the positive to be the same. And the one over here would look just like that, and so forth throughout. But remember, the electrons are moving like crazy near the speed of light, so they're zipping all over the place. And so there can be little moments where the electrons distort to one side. In this case, I show it distorting to the right side. And when the electrons distort to the right side, there'll be a little bit of partial positive, partial negative polarity here. And the electrons on this side here will repel the electrons in the neighbor, and they will polarize over to the other side. So then I'll have kind of like a little magnet here, a little electrical attraction between these two. And if we were going to boil this, we would have to overcome whatever that weak attraction is. Okay, so this is why I call them dispersion forces, because they kind of disperse around in various ways. And in the next instant, the electrons would be all distorted to the other side, and that would cause all the other electrons to distort to the other side. There would be this weak fluctuating interaction. And that's what holds these guys together, although it's a very weak interaction. So if we go down a column, just to remind you, these are all plus 7, fluorine, chlorine, bromine, iodine. They all have the same Z effective, but the electrons on the iodine are not held as tightly, and so they can distort more to one side or the other side. And that's going to induce stronger distortions over here, stronger partial positive, partial negative. And so it'll be harder to separate this from its neighbors, meaning a higher boiling point than bromine, than chlorine, than fluorine. And then if you look in a row, okay, the Z effective keeps getting bigger and bigger, And as it gets bigger and bigger, the electrons that are around this atom are held tighter and tighter. That's kind of the opposite of polarizability. Okay? Things that are less tightly held are more polarizable, more distortable, and probably should lead to stronger dispersion forces. Okay? So these guys are all in the same row, and these guys are all in the same column. So if I had another column here, it should parallel what I see over here. And if I had another row here, it should parallel what I see up above. Okay? So I have some examples here. So in this table I have a lot of diatomics. Diatomic means two atoms: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Okay, so I plotted these out, the fluorine, chlorine, bromine, iodine, in this little graph down here. And here I have the inert gases. So these are not diatomic. These are single atoms, monoatomic atoms. Helium's the smallest, neon's next, argon's next, krypton, then xenon. And so remember, the more we go down in a column, the bigger the atom, the more distortable the electrons, and the stronger the dispersion forces should be. Okay? So if we came down here, I have the actual boiling points and melting points here, but if we came down here and looked at the plot, helium is very low, almost at absolute zero. Okay, just a little bit of absolute zero, helium's going to boil. Okay, helium boils at minus 269. Absolute zero is minus 273. So this is almost absolute zero. Now if I go to neon, I have a whole extra shell. Notice what happens. The boiling point goes up. And if I go to argon, it goes up again, and krypton and xenon. So exactly what we were saying. Polarizability distorts the electron cloud more for the xenon, say, than the helium. And so it takes more energy to move a xenon away from another xenon. Now if I look at diatomics, it should be, right away we should say, well, this should be a little bit stronger interaction because I have two atoms interacting instead of just one. And so that should translate into a higher boiling point, in fact, melting and boiling point here. And so if I look at fluorine, which is in the same row as neon, the boiling point is right here. So that is a little higher. The boiling point is minus 188, and the boiling point for neon is minus 246. Okay, so quite a bit different. But if I look at fluorine in its column, fluorine is the smallest of the halogens. And when I go to chlorine, I still have two atoms, they're both chlorines, and they attract each other stronger than the two fluorines do. And so the boiling point is higher. And if I go to bromine, it's higher. And if I go to iodine, it's even higher. And you'll see this is kind of a steeper climb up here because I got two atoms interacting instead of just one. Okay, so this is kind of a simple idea. Hopefully, I've gotten across to you. I just put in here room temperature. That's typically around 25 degrees Celsius, or 298 Kelvin. And you can see that everything below here, okay, this is going to be a gas because 25 is way above the boiling point. Same here. It's way above all the boiling points of these guys. But look at what happens at bromine. At bromine, it melts below room temperature, so it would go from solid to liquid, but it doesn't turn into a gas until we get above room temperature. So bromine actually boils at plus 59. So bromine would be a liquid in our world. Now there's only one other element that is a liquid at room temperature, say 25 degrees, and you probably know what that is. That would be mercury, a metal. Now if you keep going up, notice what happens to iodine. Here's 25, but iodine still hasn't melted. So iodine's going to be a solid all the way up to this temperature right here, which is 114. That's actually above the boiling point of water. And then if we keep heating, it'll start to boil at 184. So it shows you that even though we say dispersion forces are weak, if you have enough of them, and iodine has enough, then they can become strong enough that requires still a lot of energy, 184 degrees to melt it, to boil it. Okay. And then we have our hydrocarbons. So these are all organic molecules, which we call alkanes. Okay, and alkanes are kind of the simplest organic molecule we could talk about. So I start with 1 carbon, 2 carbons, 3 carbons, 4 carbons, all the way up to, here we got 40 carbons. So this is a huge molecule. One carbon would be methane. Probably most people would call it natural gas these days. When they frack out natural gas out of the ground, it's usually mostly methane, maybe a little bit of ethane. Okay, but you see just one carbon. So can't be much dispersion forces, and we said that there is no polarity between a C and an H. This is a completely nonpolar molecule. Why would it even stick to a neighbor with no polarity? Well, the answer is there's the momentary fluctuations of the electrons that make it little partial positive, little partial negative, but it's only one carbon. Okay, so that's very weak. You can see the boiling point is minus 162. Now, if I add on another carbon there, okay, now I got two of them, so they're going to have a stronger interaction, say twice as much surface area they're interacting, and you can see the boiling point jumps up to minus 89. That's still super low, but that extra carbon took 73 degrees more to get it to boil. And if we keep going up, you could see it gets higher and higher. So our explanation for this is if we take something like hexane, 1, 2, 3, 4, 5, 6, so come over here, hexane. Okay, if we took something like hexane, we got 6 carbons in a row, and the boiling point 69. So this would be a liquid in our world. And the reason for that is we have dispersion forces between all of the different atoms, the carbons. So it's like we have 6 times the number of dispersion forces here as we had with the methane. Okay, and if we kept going up, you could see where's heptane, just one more carbon, would put it around the same as the boiling point of water. So water is a really tiny little molecule, just H2O, and it boils around 100 right here. Okay, it would take 7 carbons to equal the strength of interaction between a heptane molecule and its neighbor as to a water molecule and its neighbor because of the hydrogen bonding here. Okay, if we went up to something like dodecane, which is 12, 3, 6, 9, 12. If we took dodecane, you can see plus 216, it's getting really high. And in fact, if you were to heat some of these alkanes up to the temperatures that I show here, and there was any air around with oxygen in it, they would probably spontaneously catch on fire. Okay, possibly even explode if they had enough in the vapor phase. All right, so there's one variation we want to do with this. These are all straight chain molecules. So I have 12 carbons and I have them all in a row, but there's many ways to arrange these carbons. Okay, and you can see the trend is pretty smooth, just keeps going up, 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 up. Okay, and even though the interactions are very small for one, if you put enough of them in there, they can become quite large. Okay, so our last little example for this particular part of topic 2 is to look at chains, chains that have branches. Now, if I look at something like C3, there's only one way I can arrange C3, propane, and it has a pretty low boiling point, minus 42. If I put on another carbon and make it a 4-carbon chain, now we have a 4th carbon, so we know that it's going to go up because we have greater dispersion forces. So it went from minus 42 to 0. Okay, so it did go up just like we expect. But once I get to 4 carbons, I can arrange it in another way. I could take off 1 carbon here. Instead of attaching it to the end, I could put it in the middle. And if I put it in the middle, it turns out the boiling point is minus 12. It goes down. So this is a little strange. Why would that happen? Because there's still 4 carbons. There's still no polarity. All right. Now if I went to 5 carbons, well, 5-carbon chain is bigger than 4 carbons. I think the boiling point should go up. And it does, plus 36. So it's gone up higher because I have a greater contact surface area. Okay, so that would be like I have 3 carbons, well, that's contact, 4 carbons, greater contact surface area, 5 carbons, greater contact surface area. So that seems pretty understandable. Greater dispersion forces here than we had, say, was just 3 or 4. Now, if I come along and I take off 1 carbon and stick it in the middle, I have a 4-carbon, longest 4-carbon chain with a 1-carbon branch. Then I would have this extra branch here, and I could even do it one more way. I could take off another carbon and stick it in the middle, and then I would have 2 1-carbon branches that would look like this. And notice what happens. Each time I add that branch in, the boiling point gets lower and lower. So our explanation for this is when I make a branch, the branch kind of pushes the other molecules, its neighbor molecules, away a little bit. And so I can't quite get as good a contact as I can if they're all straight chain and they can line up right next to each other. So each branch puts a little distance between this molecule and its neighbor. And if I had two branches, then I would have even more distance. It'd be harder for all the surface of this molecule to contact the surface of this molecule here. And so if that becomes the case, then the dispersion forces are weaker. Now also the dispersion forces, just to point out, they fall off to the 6th power. So if I had something, a certain ratio, say 1/1, that would be raised to the 6th power of 1. But if I made it twice as far, as the example up here, I would have 1/2 to the 6th power. That means my dispersion forces would drop off 1 to 64. Okay, they would really fall off a lot. Now, we probably don't have 1/2 the dispersion forces here. It's probably a little closer, but it falls off a little. Okay, so branching tends to make the boiling point go down because the molecules are pushed farther away and the dispersion forces are weaker. So here's a little example to see if we can, this is a melting point. So melting points are, like I said at the start, are harder to predict. But I just wanted to give you a couple examples. There's some places where we can make a good prediction. And that is if we're looking at, say, a flexible example and a rigid example. So I have here two molecules that have the same formula. So we call them isomers, iso equal, mer unit. And so in this case, the carbons in the middle are sp, because I can see the second and third bond. So everything's linear. This is a rigid rod. Okay, this is just rigid. Now if I come down and take this CH3 and put it on the other end, now this is a single bond. I can rotate around here. So this molecule is going to be rotating like crazy. That's going to bump into the neighbors, kind of get in the way of them, so it can't get close the way this guy can. This guy has only one shape. They can pack right next to each other, and like a pack of spaghetti, dry spaghetti. They'd just be really close together, all packed very tightly. That's going to be hard to break down. Whereas this one here with the little group here, this is the ethyl group, rotating around and around, it's going to get in the way of all the neighbors, kind of push them away, and so it should be a lot easier to separate this molecule from the neighbors and break down the lattice structure. So we have two melting points, and hopefully you can see pretty clearly by what I just said which melting point goes with which molecule. So think in your head which one goes where, and then hopefully what you see is that this molecule right here is going to break down at a lot lower temperature. So this lattice structure will break down at a lot lower temperature, and that'll be the -126. These molecules are going to stay next to each other to a much higher temperature until we get up to like -32. That's still a pretty low temperature, but if you look, it's almost 100 degrees higher than this one here, just because of this little wiggle group here at the end, this ethyl group. Okay, let's take a look at this one here. So before I even say anything, think about which melting point would go with which molecule. Okay. So hopefully you got your decision. And so what we see up here, first off, this is a benzene ring. It's flat, rigid. It does not change its shape one little bit. And I have these one carbon attachments here that don't change either. Okay, there's some CH3, they rotate out here, but it doesn't really change the shape any. Okay, so this molecule is very rigid. It's not really going to have any other shape than this. This molecule, on the other hand, has all four of the carbons on one chain, and each of these bonds can rotate. So I can rotate around here, I can rotate around here, I can rotate around here. So this molecule is going to be kind of sort of banging all over the place. It's like a tail that can wiggle like a dog tail. And so this is going to push the neighbors away. If I push the neighbors away, I'm not going to have as strong interactions to break down the lattice structure. It'll be easier. So this one's going to require a lot more energy. We would interpret that as a higher temperature. And so if we look down here, we have a +79. Say that's a +80. This is a -90 or so. That's incredible. These molecules have the same formula. They have no polarity. Okay, they're nonpolar molecules. It's just the lattice structure. How well do they pack? One packs extremely efficiently, and so you have to heat it up probably almost towards its boiling point. Sometimes that's the case. If the melting point is equal to the boiling point, then we call that sublimation. But in this case, it's just a very high melting point. whereas this one breaks down very, very low, okay, because of this highly irregular chain that's wagging around. Okay, that's the end of this particular topic. I have one more on Chapter 2 that we'll look at.